Welcome back to The Explainer. Today, we're taking a look at one of the most incredible, continuous journeys happening right under our feet and way above our heads. We're talking about Earth's water cycle. But, we're not just going to do the standard grade school recap of rain falling from clouds and rivers running to the sea. We're going to go way deeper. We're examining this closed loop from the absolute deepest hidden layers of the Earth's mantle, literally all the way up to the frozen edge of space. So here's our roadmap for today's deep dive. 1. Our planet's water inventory. 2. The deep underground ocean. 3. Nature's natural filtration system. 4. Replicating water cycles in space. And 5. Is Earth losing its water? By the end of this explainer, we're going to tie geology, hydrology, aerospace engineering, and astrophysics all together into one really cool story. All right, let's jump right in. Section 1. Our planet's water inventory, measuring the blue planet. To really understand this whole loop, we've got to set a baseline. Just how much water are we actually talking about? Well, take a second and look at this number. 332.5 million cubic miles. That's the total volume of all the water on our planet. To put that completely massive figure into perspective for you, if you took literally every ocean, ice cap, lake, river, underground aquifer, and all the vapor in the atmosphere, and you rolled it up into a single sphere, that giant ball of water would be about 860 miles across. But the way that massive volume actually breaks down is honestly a bit of a shock. Check this out. 96.5% of all that water is just sitting in our oceans as saltwater. Only about 2.5% of the entire planet's water is fresh water, and it gets crazier. Because of that tiny 2.5% slice, the vast majority is locked up in frozen glaciers or buried way too deep underground to reach. So all that fresh surface water we see every single day, the rivers and lakes we actually use, it makes up a tiny, tiny fraction of 1% of the whole shebang. So that's the surface and the ice. Let's move on to section 2, the deep underground ocean, water inside the mantle. Okay, beyond the everyday evaporation and rain we're used to, there is a much, much bigger microscopic system pulling the strings behind the scenes. It's called the geologic water cycle. Over millions of years, Earth's tectonic plates slide beneath one another, a process we call subduction. And as these giant oceanic plates get dragged down into the mantle, they take an immense amount of water right down with them. Now, if this was a one-way street, our oceans would have dried up billions of years ago. But it's a closed loop. All that trapped water eventually gets blasted back up to the surface through volcanic eruptions at mid-ocean ridges. And this perfectly illustrates just how much water is actually hiding down there. About 400 miles beneath the crust, geologists have found a mineral called ringwoodite. And because the pressure down there is just absolutely intense, this rock acts like a giant sponge, trapping water molecules right inside its crystal structure. Get this, researchers estimate that this layer of ringwoodite could hold up to 3 times the volume of all our surface oceans combined. It completely flips the script on how we view our planet. It actually suggests that our oceans might have originally seeped out from inside the Earth itself, rather than just crashing here on icy comets. So we've gone deep underground. Let's travel back up to the surface for section 3, nature's natural filtration system, cleaning the cycle. Since accessible freshwater is so incredibly rare, nature has to work overtime to keep it clean enough to sustain life. And nature really is the ultimate water filter. It works in these brilliant linear steps. First, rain hits the ground and undergoes soil percolation, seeping down through layers of dirt and rock. Next, it hits wetlands or marshes. People often call these environments nature's kidneys because the plants and the slow-moving water naturally absorb excess nutrients and trap muddy sediments. Finally, the water drains into deep underground aquifers, getting stored in gravel and rock to create some of the purest drinking water on Earth. Let's zoom in on that very first step for a second, soil percolation. Dirt might seem, well, basic, but the mechanics at play are genuinely elegant. First, it's a physical sieve. The tiny little pores in the soil physically block solid particles and pathogens from passing through. But it's also a chemical filter. A lot of soils, especially clay, have a natural negative chemical charge, so they act like a magnet, attracting positively charged pollutants and locking them in the dirt so they never hit our groundwater. And finally, it's a biological filter. There are highly specialized bacteria living in that soil that literally eat and metabolize trapped organic pollutants, spitting them out as harmless byproducts. It's a beautifully efficient system. And because nature's water cycle is such a masterpiece of engineering, when we decided to pack up and live in the vacuum of space, we literally had to copy it. That brings us to section 4, replicating water cycles in space, the ISS microcycle. Up in space, every single drop of water is priceless. Rocketing heavy tanks of water up into orbit is crazy expensive and logistically a nightmare. So to survive on the International Space Station, astronauts rely on a heavily integrated piece of tech called the Environmental Control and Life Support System, or ECLS. Basically, NASA took Earth's atmosphere, wetlands, and soil filtration and shrunk it down to fit inside a space station. This system captures the moisture from the crew's breath. It sucks the humidity of their sweat right out of the cabin air, and yep, it even collects their urine. And the reason we are talking about this is because of a massive recent milestone, 98%. The life support teams over at NASA finally hit a 98% water recovery rate. That means if you launch 100 pounds of water up to the station, 98 pounds of it is continuously recycled in a closed loop. It just keeps going around and around. That is an absolute game changer, and it's exactly the kind of tech that makes long, deep space missions to places like Mars a real logistical possibility. So how exactly did they push that recovery rate all the way to 98%? Mostly through a relatively new piece of hardware called the Brine Processor Assembly, or BPA. See, the older systems used to leave behind this salty urine brine that still had a little bit of water trapped inside it. The BPA takes that leftover brine and squeezes it into a specialized dual-layer membrane bladder. They blow warm, dry air over it, which forces that stubborn remaining water to evaporate right through the membrane. It's a process called perevaporation. The air catches the moisture, leaving only bone-dry salt behind. And after all that reclaimed moisture runs through a series of catalytic reactors and filters, the resulting drinking water is actually significantly cleaner than the tap water you're probably drinking right now. Okay, so we figured out how to close the loop inside a tin can floating in microgravity. But what about our actual home planet? Let's pan out from the human scale to the cosmic scale. For section 5, is Earth losing its water? The cosmic leak. Well, the short answer is yes. Gases at the very top edge of our atmosphere can and do leak out into outer space. It happens through mechanisms known as atmospheric escape. First off, you have thermal escape. Basically, if an atmospheric molecule absorbs enough extreme heat from the sun, it speeds up, and if it moves fast enough to beat Earth's gravitational escape velocity, boom, it flies off into the void. Naturally, lighter molecules, like hydrogen, escape a lot easier than heavy ones. Then there's photochemical escape, where intense UV photons from the sun literally shatter water molecules apart in the upper atmosphere. And finally, charge exchange. This is when high-energy particles from solar winds violently slam into atmospheric gases and just strip them right away. And you don't just have to take my word for it, we can actually see it happening. Look at this ultraviolet image here. You see that massive halo surrounding the Earth? That's hydrogen. And many of those atoms, the exact same hydrogen atoms that make up our H2O, are actively hitting escape velocity right now, leaking directly out of the exosphere and bleeding into deep space. Let's actually do the math on this cosmic leak, because it's fascinating. Every single year, Earth's gravity naturally pulls in about 40,000 metric tons of space dust and meteorites, so we are gaining some mass. But because of those atmospheric escape mechanisms we just broke down, Earth is simultaneously losing about 50,000 metric tons of mass, mostly hydrogen and helium, every single year. When you balance those two numbers out, the reality is kind of wild. Our planet is literally shrinking. We're on a cosmic weight loss program, losing more of our mass to the void than we're sweeping up. Now look, there is zero need to panic today. Our oceans are not going to vanish by next Tuesday. But astrophysics does tell us that as our sun ages, it gets continuously brighter and hotter. Fast forward about 1 billion years, and the sun is going to be roughly 10% brighter than it is right now. That extreme heat is going to dramatically spike the water vapor in our upper atmosphere, pushing this atmospheric escape into overdrive. The UV light will shatter the water, the hydrogen will bleed out into the dark, and eventually our oceans will simply dry up. It leaves us with this incredibly profound thought. The water that gives us life, the water that cycles all the way from the deep mantle up to the clouds, it's just a temporary gift. So what exactly is going to remain of our beautiful blue planet when that closed loop finally breaks open? It's a fascinating question, isn't it? And honestly, it makes you appreciate every single drop of rain just a little bit more. Thanks so much for joining me for this explainer, and as always, keep looking closely at the world around you.